Hello and welcome to section 3.2 on the derivative as a function. In this video, we will discuss the derivative of any point on a curve f, and we will begin to develop differentiation rules, allowing us to skip limit calculations when differentiating most functions. In section 3.1, we developed the derivative of f at the point p to be the slope of the tangent line at p. The function f has many points p, and at each one we can attempt to calculate a derivative. Keep in mind that a derivative is a limit, and like limits, the derivative may not exist. By connecting each x value a with the derivative f prime of a, we create a function whose domain consists of the x values where f is differentiable. The derivative function f prime of x is found by taking the limit as h approaches 0 of the difference quotient on the interval x to x plus h. For example, take the inverse function f of x equals 1 over x. We can calculate the derivative f prime of x by taking the limit as h approaches 0 of the function's difference quotient. Rewrite the numerator as a single fraction and simplify the expression. We then calculate the derivative function f prime as -1 over x squared. The domain of f prime, the derivative function, is all real numbers except for 0. We can visualize the derivative function by considering ants walking along our curves once again. As an ant crawls along the function, the slope of the direction that the ant walks along the curve is the derivative at that point. Along this segment of the curve, the ant is crawling downwards, so the slope of the tangent line is negative. Notice that the graph of the derivative is negative along the highlighted interval. At this location, the ant is level. It is horizontal. Notice that the graph of the derivative is 0 at this location. Along this interval, the ant is crawling upwards, so the slope of the tangent is positive. Notice that the graph of the derivative is positive along the highlighted interval. There are two common ways to denote a derivative. We've been using the notation of Lagrange. That is, we've been writing the derivative of the function f as f prime and the second derivative of f as f double prime. For higher derivatives, we use parentheses in the power. That is, the 99th derivative is f raised to 99 in parentheses. Lagrange's notation is quick to write, however it is generally too inaccurate. The notation of Leibniz treats derivatives like an operator. If we wish to take the derivative with respect to x, we write d over dx. So the function y equals f of x can be described as d over dx of y, or d over dx of f of x, or dy over dx, or df over dx. The way we read the notation of Leibniz is as the derivative of y with respect to x, or the derivative of f with respect to x. This notation originates with the concept that derivatives are the limit of the slope between 2 points a and b, as b approaches a. That is, the slope is the change in y over the change in x. Leibniz notation will be very useful when we have multiple variables to consider, in that it specifies precisely which variables we are changing. They are noted in the denominator, and in which variables the corresponding change will occur, they are noted in the numerator. In this section, we develop the first rules that will allow us to calculate derivatives without calculating limits. Functions can be very complicated and do not necessarily follow a set pattern. The only requirements for a map to be a function is that every input can have at most one output. In all but a handful of cases, the functions that we deal with are elementary functions. As outlined in the slides of section 2.4, an elementary function is constructed from a collection of basic functions using composition and arithmetic operations. The basic functions consist of constants, powers and roots, exponentials, logarithms, the 6 trigonometric functions, and their inverses. The goal of the next few sections is to calculate derivatives of the basic functions, and to discover how to find the derivative of all elementary functions by learning the rules of differentiation for composition and arithmetic operations on functions. For example, Assume that both f and g are differentiable functions at a. That is, f prime and g prime of a both exist. Is the function f plus g differentiable at a? Does f plus g prime at a exist? Well, we have to go back to the limit definition. Take the limit as h approaches 0 for the difference quotient of f plus g on the interval a to a plus h. Since f plus g at a equals f of a plus g of a, we can rewrite the numerator as f at a plus h minus f at a, plus g at a plus h minus g at a. We can then break the fraction into two. The first fraction is the difference quotient of f, and the second is the difference quotient of g on the interval a to a plus h. Since we know that f and g are both differentiable at a, both quotients' limits exist as h approaches 0. Hence, we can use the limit law for sums to show that the derivative of f plus g at a is the derivative of f at a plus the derivative of g at a. We have just proved the summation rule for derivatives. If the derivative of f and g both exist at a, then the derivative of f plus g at a equals the derivative of f at a plus the derivative of g at a. It doesn't matter whether you add or differentiate first, the result is the same. In this section, we will discuss two rules for differentiation. The sum and difference rules for differentiation states that if functions f and g are differentiable, then the derivative of the sum or difference equals the sum or difference of the derivatives. The order is irrelevant. The constant multiple rule for differentiation states that if c is a constant and f is differentiable, then the derivative of c times f equals c times the derivative of f. You can multiply a constant in a function before or after you take a derivative, and the result will be the same. In the next section, section 3.3, we look at the derivative of products and quotients of functions. While in section 3.7, we look at the derivative of composition of functions. The differentiation rules deal with derivatives of functions constructed from basic functions. But what are the derivatives of the basic functions? Let's take a look at a few. The derivative of a constant function c is always 0, as constant functions have zero change among their y values. Looking at the limit definition of the derivative, the numerator is immediately 0. For functions of the form x to the n, where n is a constant, the power rule states that the derivative of x to the n is n times x to the n minus 1. Basically, the derivative of x to the n, you bring down n and multiply in front and subtract 1 from the power. In particular, the power rule implies that x to the n is differentiable everywhere n minus 1 is positive, and differentiable at all values except for 0 when n minus 1 is negative. Let's combine these rules. For example, we will find the derivative of the polynomial function f. Since all of the major parts, x cubed, x squared, x, and 1, are all differentiable by the power rule, we can use the sum and difference and the constant multiple rule of differentiation to simplify our calculation. The derivative, f prime, is 3x squared minus 6x plus 1. We still have a lot of basic functions left to differentiate. In class, we will differentiate exponential functions. In section 3.6, we will differentiate trigonometric functions. In section 3.8, we differentiate inverses of functions. And finally, in section 3.9, we differentiate logarithmic functions. You've seen the basics. Now work towards mastery through practice and study.